No discussion of QuickSort is complete without bringing up its one fatal flaw. If all your input values are identical, then performance degrades to O(n squared). Well, that seems to be widely accepted as that's just what QuickSort does, but of course we're here to ask the age-old question, can we do better? Hello and welcome back to another video. Now, as always, for the sake of those who are just joining us, we'll do a very quick recap of partitioning, which is of course the core idea behind QuickSort. If you've already seen that, if you're familiar with that, feel free to open up the video description or use the chapters on the seek bar to jump ahead. So let us very quickly recap on partitioning. Now, remember the way in which QuickSort works is that we pick a pivot. Then what partitioning essentially does is it rearranges the elements in the list so that the items smaller than a pivot go on its left and the items larger than a pivot go on its right. There is one crucial property that I need you to notice here, and that is the pivot element itself is already in its final sorted position. That means if we were to sort the entire list, 5 would be right here and nowhere else. The reason for this is because, well, if we were to sort the entire list, all the items left of the pivot are still going to be smaller than it, right? That's what partitioning did in the first place. So they remain left of the pivot, just in a slightly different order. Same for the elements larger than the pivot. If we were to sort the list, again, it's the same 4 items in those positions, the pivot doesn't have to move. So the pivot is in the final sorted position. Now, going back to our original list, how QuickSort works is that it will recursively continue to do partition on each of the sublists that were created here. So we always start on the left sublist if it's available. In this case, we'll pick the first element 3 as the pivot. This again creates left and right sublists. So we continue the process recursively on the left sublist. In this case, no further left sublists were created, but we do have a right sublist here, which again, we'll repeat the process for. Notice that every element has to have its turn being selected as the pivot because again, being selected as the pivot means you get put in the final correct position. So this process repeats until every element has had its go. Now we have a sorted list. With regular partitioning, QuickSort tends to look something like this. You'll have a set of sublists, they'll get broken down further and further with partitioning. And yeah, you get O(n log n) behavior here because we have n items. They're being processed across approximately log n steps. So n times log n. The worst case comes about when this happens, when you are unable to partition the list repeatedly. If this list has n items, since for each step we really only have a pivot, in this case providing us with no left sublist and everything in the right sublist, then we'll need to process this over n steps as well. That's why we say the worst case is O(n squared). N items processed n times, and that of course isn't good. So that's what we've always accepted QuickSort to be. But of course, the question is, can we do better? And turns out we can if we take inspiration from the Dutch national flag. That's this flag right here, and there are some interesting reasons why this is the flag that was chosen. This idea apparently was first proposed by Edzard Dijkstra. Yes, the same Dijkstras you know from graph algorithms. And yeah, the man's Dutch, so this works out nicely. But yes, the idea is that just like the flag, there are now 3 partitions instead of 2. Instead of just having a pivot element and then there's stuff smaller on one side and stuff larger on the other side, we're now going to create 3 partitions: smaller, larger, and equals. Let's see how that helps us. So again, the way in which the Dutch national flag partitioning algorithm works is we get 3 partitions instead of 2. The partition on the left contains values smaller than the pivot, and the sublist on the right contains values larger than the pivot, while all the values in between, these are the values that are equals to the pivot, so they have the same value. This gives rise to something interesting, and to understand that, let's go back first to our regular old partitioning, which we've seen earlier. Remember, if you have a pivot value and you have all the items smaller than it on the left and all the larger items on the right, then we conclude that the pivot is already in its final sorted position. Now, what's interesting about this list is that we can draw the same conclusion, right? All the smaller items are on the left, all the larger items are on the right. what's in the middle, of course, they are sorted. This means that we don't have to check these values anymore. They are already in the correct position. For our next pass of QuickSort, we only need to process the left and right sublists. The entire middle sublist can be ignored because it's already in place. All of a sudden, QuickSort becomes robust against duplicate inputs. This was previously the worst case scenario, right? That's the worst thing that could happen to QuickSort. But now, thanks to the fact that we just ignore that equals sublist in the middle, this turns out to be the best case instead, because all those elements in the middle just don't have to be processed. So now that we understand why this is a good thing, let's go ahead and get into the trace. So here's our input list now, lots and lots of duplicate elements as you can see. Let's go ahead and start with our trace. Just like with regular partitioning, we need a pivot. But the difference is, we're not so interested in the pivot index, the specific element itself. We are more interested in its value. Since we're allowed to have duplicates, we don't need to have a specific pivot. We are really more interested in separating things by the value of the pivot. Let's start by populating several indices or pointers that will point to specific elements. Now, I'm going to name them in this manner. This one is called less than, which I'll shorten to LT. This one is called greater than, I'll shorten it to GT. And we have an equals pointer as well. And at the end of all this, at the end of the trace, these three pointers will mark out the positions of where each partition actually is. I should also mention now that the equals pointer is the one that is sort of the main comparator, but all three of these pointers can move, and independently too. So let's actually begin with our trace. We're going to take the pivot value and we're going to compare it against the element that the equals pointer is pointing to. So three possible things can happen here, the first of which is the values are equal. If the values are equal, it's very simple, we simply move the equal pointer forwards, and that's it. Now, let's look at another case here. We're comparing it against 7. Now 7 is larger than our pivot 4. So here's what we do. We perform a swap between the value at the equals pointer and the value pointed at by the greater than index. So we swap the two values, and then we move the greater than pointer inwards. So we're essentially creating a sublist here, right? This 7 is definitely greater than the pivot value of 4. So we're going to build our sublist coming in from the outside like this. In this case, we move the greater than pointer forwards, and that's it. Notice that we've swapped a fresh value over to the equals pointer, right? So we haven't actually performed this comparison. That's why we don't want to move this pointer forwards, okay? Our next step is simply to just take this 4 and compare it against 2, the new element that was placed here. This nicely brings us into the third possible case, where the element you see here is smaller than the pivot value. In this case, here's what we do. We'll swap this value with the value pointed at by the less than pointer, like so. This brings this 4 into view here. Now, we've already processed this just now, right? It came from the left. So we can move our equal pointer forwards. At the same time, this 2 also belongs to the less than sublist, right? We've compared it already, we know where it's supposed to go. Therefore, in this case, we move 2 pointers forwards, the less than and the equal pointers, like so. Alright, so these are your 3 cases. Each one of the cases will involve potentially different swaps and different pointer manipulations. Like I said, you've actually already seen everything, but let's go ahead and complete the trace anyway. The value 2 is smaller than 4. Therefore, we need to perform a swap and we move both of these pointers forwards. 4 and 4 are equal, so we don't have to do anything but move these pointers forwards. 6 is larger than 4. So we perform a swap between those two 6's, we move the greater than pointer inwards, but remember, the equals pointer does not move. The next 6 which comes into position is still larger than 4, so again, we swap and we move the greater than pointer inwards. Same goes for 7 here, again, we swap. 4 and 4 are equals this time, so we just move this forwards. 2 is smaller than 4, so we send it to the left. 4 and 4 are equal, so we move forwards. 6 is larger than 4, so we swap it to the right. 4 and 4 are equal, so we move forwards again. Now, these two pointers are overlapping now, so this should indicate to you that we're nearly done. But we're not entirely there yet, right? The value 3 still needs to be compared against 4. we'll find that 3 is smaller, so it gets sent to the left, and we move the less than and equal pointers forwards. Now that the equals pointer has crossed the greater than pointer, we're done. We're properly done now. This is the state of our list. Again, we'll find that all the equal elements are in the middle. Because the values on the left are smaller and the values on the right are larger, these 5 elements have been sorted. They're in their final correct position. This leaves us with our left and right sublists. Well, we can repeat this process again. To keep things simple here, I'll just pick the first element as the pivot. We'll do our respective sorting and movement of elements as in this case. Again, everything that matches the pivot value is put in place, so we can move on to our next step with very few elements left. In fact, they're all equal, right? So they become the pivot, they get put in place, and we're done. This is our final sorted list. Observe now that when we have many duplicate values, we can discard a whole bunch of them at once. We never need to reprocess them, and we can come to this conclusion very quickly. Let's look at the code, and the code for doing this is surprisingly simple as well. To start off with, we will create our 3 pointers in the exact same manner as we've done previously. Then we'll start our loop. Remember, this loop needs to keep running until equals, which is like a running variable, right? It crosses with the greater than pointer. Then we write out our 3 cases. The first case is the simplest one, where if the value in the list at the equal pointer matches the pivot value. If it does, we just move this forwards. We don't have to do anything else. Otherwise, if the value there is greater than the pivot, then it needs to get sent to the back of the list. So this is a swap that we perform, and the greater than pointer moves backwards. So we do a subtraction or a decrementation here instead. In the final case, where the value is smaller than a pivot, again, we'll perform a swap with the less than item. And remember, this time, we have 2 pointers to move forwards. By the time this loop is done running, we will have rearranged the elements so that they fall into our Dutch national flag pattern. Smaller items on the left, equal items in the middle, and larger items on the right. Of course, we need to convey this information somehow. For a regular partitioning algorithm, what we do is we return the final position of the pivot. In this case, since there are 2 pointers involved, we need to return the 2 of them. You'll notice I've done a little bit of additional arithmetic here, and here's why. This is our list at the end of our partitioning operation. You'll notice that the less than and greater than pointers are both pointed to the equals partition. What I would really like to do is I would like to shift them like this so that the less than pointer points to the last element of the smaller partition, the greater than pointer points to the first element of the larger sublist. This will make things a little bit easier for us when we do QuickSort later on. But before we can do that, let's make a small amendment. You see, typically, we don't want to just operate on the entire list, right? In this case, you'll realize that our pointer always goes to the first element and the last element. What we really want to do is we want to allow the user to specify a certain set of start and end indices. And the reason why we want to do that is because once you have your partitions, once you go further with your QuickSorts, you only want to act on selected sublists within the overall list itself. So our changes are very slight. We take in these 2 numbers as parameters, but what we'll do is we'll use them as initial values for our 3 indices. Again, your less than and equal indices or pointers need to point to the start of your array. In this case, it will point to the start of our sublist, whereas the greater than index will point to the end of it. Now what you can do is you can just process one small part of your list rather than having to process the entire list at once. So, how do we do QuickSort? Of course, the algorithm has to be slightly modified. Our standard QuickSort expects exactly 1 pivot, but in this case, we actually have 2. So here's what happens when you perform QuickSort. Let's assume that start and end indices are provided. So within your entire list, we are sort of selecting a sublist of elements to process. First, we'll determine the pivot value. Observe, we're interested in the value, right? Not the index. So what we'll do is we'll just read off some value for use as the pivot value. For simplicity's sake, we'll just use the first element, even though when we actually implement it later on, we'll use a random element just to, make it a little bit more robust. Regardless of your approach, the point is to pick a pivot value. Then we'll perform our partitioning. We'll give it the entire list, but also the start and end indices. We'll use the pivot value that has been defined here. Now, after this partitioning has been performed, 2 numbers will be returned to you. The first number indicates where the left sublist ends, the second number indicates where the right sublist starts. So with this diagram, you can see how it sort of guides us to move on to our next two recursive calls to the same function. So our first recursive call will go from the start index up to the left index, whereas our second recursive call will go from our right index up to our end index. So what this does is, it still gives you your two sublists, but we get to ignore more than one element because more than one element has already been sorted by this process. So that's the power of doing this variant of QuickSort. Of course, don't forget your base case. If your indices cross, then there are no values in the partition and you don't have to go further. Let's look at the actual code itself. This is the code written out in Python. Yeah, it's largely the same, and of course, Python code looks a little bit like pseudocode, so it's not all that different from what we've seen in the slides. For partitioning, we initialize with our indices, which are passed in as parameters. We'll have our loop, again making sure that it keeps running until the equal and greater than pointers actually cross. From there, we'll check our three conditions. Once the loop is complete, we'll return where the actual partitions are, doing the arithmetic to sort of adjust and offset everything. The actual QuickSort itself is very similar, even though I'm doing one additional step here to find a random pivot index and extract out that value. After doing partitioning, I'll make two more recursive calls to the function itself. We'll keep going until we hit our base cases. I've even added an extra base case here. I don't think that's actually necessary, but yeah, that's just defensive programming for you. No surprises here that I'm able to, well, run the code and have it sort the list. This list happens to have no duplicates, but yeah, even if I were to actually modify this list so it matches the list that we have in our slides, again, running the code, you will get the values in a sorted order. So this definitely works. In terms of time complexity, the Dutch national flag partitioning changes surprisingly little, and this is especially true if you look at it just as a partitioning algorithm. I mean, after all, we're gonna have to visit all n items to perform our partitioning, so yeah, it's pretty much identical compared to other partitioning algorithms. But what about the impact on QuickSort itself? Again, no surprises here, it's almost entirely the same. In the average case, it's still going to be n log n, because you're still gonna have n items, you're still gonna create partitions, it's still gonna take log n steps. Where it stands out is in fact in the constant factors. The n log n asymptotic timing isn't going to change, but the number of sort of little steps that you do along the way will sort of add up differently, and that is dependent on the input data. If you have many duplicates, then a Dutch national flag partitioning is better, because what it can do is it can fix a whole bunch of pivots at once, like we've seen earlier. You sort of get an optimization there because for every step, you get to ignore many of the elements, and you only need to process less elements with each step. On the other hand, if your list has little or no duplicates, then we're actually doing a little bit of extra work in our Dutch national flag partitioning in comparison to some of the more traditional partitioning schemes like Hor's or Lomuto's algorithm. We'll still have to properly follow the code, right, and check to see if elements are equal, even though we know there are no such elements. What this tells us is that in the average case, we don't actually know whether Dutch national flag partitioning is better or if just regular partitioning is better, because that is dependent on your input data. When it comes to the worst case of O(n square, again, that's no difference, but the good news is that with Dutch national flag partitioning, what we've done is we've taken away one condition in which we'll end up with O(n square, and that is when your list is entirely identical. This partitioning scheme makes our algorithm robust against duplicate elements. At the same time, if we were to also pick a randomized pivot, then sorted inputs and sort of adversarial and maliciously constructed inputs will also not trip us up. With these two cases dealt with, the possibility of having this O(n square situation is incredibly unlikely. The randomized pivot selection has to go really wrong for you to get O(n square time, right? The likelihood is extremely low, and of course it gets lower the larger your list. So the Dutch national flag partitioning algorithm does not make the O(n square case go away. Unfortunately, there's nothing we can do to really make it disappear. But with that said, we've made it harder and harder to reach, and that's a victory too. Of course, there's one more case we haven't discussed, and that is the best case. Now, turns out there is something interesting to say here. Let's think about, for regular QuickSort, what the best case actually is. If you're doing one element partitions, then the best you can hope for is that you are able to create perfect partitions each time. While that's great, well, you still have to do recursive partitioning, right? So for regular QuickSort, the best case is O n log n. However, if you're using Dutch national flag partitioning, the best case is now when all the elements are identical. Notice, this used to be the worst case, right? But again, with this new attempt at partitioning, we are not afraid of duplicate elements. In fact, this becomes the best case because now we get to fix all our elements, giving us no left sublist and no right sublist, and no more recursion or computation required. We can terminate immediately after one pass, making the best case now O n. The big O notation has actually improved. And there you have it. We've now made QuickSort very close to perfect. Unfortunately, we can never truly get rid of the O n square, but we have made it much harder to encounter, and I guess that's a step forward. Now, out there, QuickSort gets taken further. There are many other things you can do to sort of fine-tune the performance and to get the very best out of what conceptually remains to be QuickSort. But yeah, we are pretty much there. But yes, that's it. Hopefully this was an insightful behavior. Hopefully it shows you the exciting world of computer science and how interesting it is when it comes to, just finding different ways to solve problems. Thank you very much for watching, and until next time, you're watching 0612 TV with NERDfirst.net. Hey, have I been helpful? Want to see this channel grow? A PayPal donation or a super thanks would be incredible. Of course, you can always share the video, comment on it, like it, and subscribe. You know the deal. Thank you once again, and I'll see you next time.